So we are continuing with 6.2 series solutions to DEs. Here's our next example. We're going to find the first three non-zero terms of y1 and y2 using sigma notation. And here's our DE, y double prime minus 1 plus x times y equals 0. So let's start off with just recalling what y, y prime, and y double prime are going to look like. So y is the sum from n equals 0 to infinity, cn x to the n. Y prime is just the term-by-term derivative of that. So n cn x to the n minus 1. The catch here is that we sum from n equal 1 to infinity. We actually want to exclude that n equals 0 term, because if we think about what that n equals 0 term would be, it would look like 0, c0, x to the negative 1. And we want to avoid that because that has a negative exponent that's going to throw a wrench in our algebra. It's valid to exclude it because it is 0. So it's just more convenient to start that series at n equal 1. Similar story for y double prime. We're going to see that we actually start the summation there at n equal 2. The term-by-term derivatives are going to look like n times n minus 1, cn x to the n minus 2. And let's think for a second about why it's valid to start that summation at n equal 2. So what the n equals 0 term would look like if we had included it, let's just try subbing in n equals 0 here, be 0, c0, x to the negative 2. And if we think about the n equal 1 term, it would be 0, c1, x to the negative 1. So the reason we want to exclude those, or motivation for excluding them, is that they've got negative exponents. And those exponents are going to make life difficult in terms of the algebra. But the reason why it's valid to exclude them is because they are 0. So it's fine to just discard them, and y double prime is still written correctly if we start our summation at n equal 2. So from there, let's plug into our DE. Our DE looks like y double prime minus 1 plus x, y equals 0. Well, what's going to happen here is we're actually going to need to distribute, and it might be better to do that before writing down our series. So we've actually got y double prime minus y plus xy equals 0. Or better, let's call that y double prime minus y minus xy equals 0. Okay, so now let's sub in. We've got the sum from n equal 2 to infinity, n times n minus 1, cn x to the n minus 2, minus y, which is the sum from n equals 0 to infinity, cn x to the n, and then minus x times y. So we'll just copy out, again, the appropriate series there, and all of that is equal to 0. Okay, so the one little adjustment we should make here is that x that's sitting out in front of this last series here. Let's actually bring that into the series. So I'm going to cross off the x here. This actually becomes an x to the n plus 1 then. So now we're going to do the thing where we adjust the powers, the exponents on these series. We want to make it so that all three series have the same exponent. And we're going to use a change of variables to do that. So for this first series, k is going to be the new name for our exponent. So k is equal to n minus 2. And we need to figure out what k values we're going to be summing through. So if n is 2, that implies k is equal to 0. Now, for the sake of the rewrite that we're going to do in the next step, it's nice to actually solve this little equation here for n. So if k is equal to n minus 2, then n is equal to k plus 2. So we'll just store that away for a minute. So we're going to do the same kind of reasoning for the other series. For the middle series here, k is equal to n. That is starting at n equals 0. So that implies that will be starting at k equals 0 when we rewrite it in terms of k. And for the last series, k is equal to n plus 1. That was starting at n equals 0. So that implies it's going to be starting at k equal 1 when we write it in terms of k. And for the sake of the algebra we're going to do in the next step, we want to solve this little equation here for n. So if k is equal to n plus 1, then n is equal to k minus 1. And we'll just keep that in mind for our next step. So the plan of attack now is to rewrite all these series using k, and the rule is that all our series need to start at the biggest k value. So we need to look over the starting k values for all three series. Was k equals 0 for the first series, k equals 0 for the second series, but k equal 1 for the third series. So the biggest out of all of those values, biggest out of 0, 0, and 1 would be 1. So all our series need to start at the value k equal 1. So now we have a little bit of an issue because we said that that first series should be starting at k equals 0, meaning there's an extra term in that series. So the plan is going to be, we're going to have to pull out that k equals 0 term. It's just going to have to hang out in front of the series. And then that series can go from k equal 1 to infinity. So we'll have a k equals 0 term, and then plus we'll have the series from k equal 1 to infinity. And same kind of idea with the second series, because that was starting at k equals 0. Now there is a minus sign in front of that, so we should actually be writing minus whatever the k equals 0 term is, and then we'll be subtracting the series that goes from k equal 1 to infinity. Finally, for the last series, that was already starting at k equal 1, so there's no extra terms that need to be sitting out in front of that series. We're just able to go minus the sum from k equal 1 to infinity, and then all of that is going to equal 0. So let's see if we can work through the algebra systematically here of what these different terms are going to look like. So we're looking at the first series, and we're thinking about how do we get the k equals 0 term? Well, another way of thinking about the k equals 0 term is that it's just the first term of that series. So if we look back here, yes, the series is written in terms of n right now, but if we just sub in that first n value, sub in n equal 2 into that series, that's going to tell us what that first term is. And we've already said that n equal 2 is equivalent to k equals 0. So whether you think of that as the k equals 0 term, or whether you think of that as the n equal 2 term, it's just the first term in the series. So let's sub in n equal 2 and see what happens. We'd have 2 times 1, so 2, c2, x to the 0. Okay, well, let's just call that 2c2. And then we've got the sum from k equal 1 to infinity. And we have to think about what's the relationship between n and k. We said back here, we said that n is equal to k plus 2. So let's sub in k plus 2 in the place of n, and we'd have terms that look like k plus 2 times k plus 1 c sub k plus 2 x to the k. Okay, so that's the first series dealt with. Now we're moving into the second series. We need to subtract off that k equals 0 term. And another way of thinking about that k equals 0 term is just that it's the first term of that series. So what is the first term of that series? Well, that series started at n equals 0. So if we sub in n equals 0 to that middle series, c0 x to the 0. So we don't really need to write the x to the 0. We can just write minus c0. And then we're going to have minus this sum from k equal 1 to infinity of whatever the appropriate terms are. Now, for that middle series, k was equal to n. So to get that written in terms of k, we're just replacing the n with a k, and we get terms that look like ck x to the k. Okay, now last series, we said that's going from k equal 1 to infinity. There are no extra terms to deal with for that series because it was originally starting at k equal 1. So it's just a matter of figuring out what the terms look like. And for that last series, we had said the relationship between k and n was that n is equal to k minus 1. So let's replace n with k minus 1. Our terms are going to look like c sub k minus 1, and the power of x was x to the n plus 1, which is otherwise known as x to the k. So there we go, we have this big expression, and that's equal to 0. So from here, things are going to get much easier to write down. If we just collect all our extra terms at the beginning, we've got 2C2 minus C0. Then we've got three series that all go from k equal 1 to infinity. So we can collapse this just into a single series and notice that each of those series have the power x to the k in there. So we're going to be able to just factor that out at the back. And let's work on writing down our coefficients. So we'd have k plus 2 times k plus 1 c sub k plus 2 minus c sub k minus c sub k minus 1. That's all times x to the k, and that's equal to 0. So now we're really getting somewhere. The plan from here is that we are going to set all the coefficients equal to 0. The reasoning behind this is that we have this power series on the left side, and that's equal to 0 for all x values. So whenever that setup happens, that means that each and every coefficient in the power series must be equal to 0. So let's look at our constant term over on the left side of the screen. Must be the case that 2C2 minus C0 is equal to 0. That's our constant coefficient, so that's got to be equal to 0. And what we like to do is just solve for the higher coefficient in terms of the lower coefficient. So that's telling us that C2 is equal to C0 over 2. Okay, now let's look at the coefficient that we've got inside the square brackets. That's also going to have to equal 0. So k plus 2 times k plus 1, c sub k plus 2, minus ck minus c sub k minus 1, that stuff there has to equal 0. And the plan for this is that you always want to solve for the coefficient with the highest index, or the largest index. So we want to solve for c sub k plus 2. All right, so let's bring the c sub k and the c sub k minus 1 over to the other side. Those would both have coefficient positive 1 once we brought them over to the right side. And then we're dividing by k plus 2, k plus 1. Now the k values that would be valid to go in here would be whatever k values our series is being summed through. And that was k values that were at least 1. So the plan here is that sequentially plugging in our k values 1, 2, 3, etc., those are going to generate our coefficients C3. So by subbing in k equal 1, we get C3. By subbing in k equal 2, we get C4. And depending what the question's asking, we can decide how many coefficients we want to generate. All right, so let's take stock of where we are at here. I'm going to put this stuff at the top of the screen, just in a box. That part there is called our recurrence relation. So that tells us what our coefficient C2 looks like, and then it tells us what our higher coefficients C3, C4, C5, etc. look like in terms of previous coefficients in the power series. And might be good to just point out on the side here, C0 is going to remain unknown. The only way we could figure that out is if someone had told us what the value y of 0 was in the question, but we weren't given any initial conditions. So we will never know C0, neither will we know C1. That will remain unknown. The only way we would figure out C1 is if we were told the value of y prime of 0 in the question. So C0 and C1 are unknown. Up here we've got our value of C2 in terms of C0, and our plan is just to get a few more coefficients figured out using this recurrence relation that we've got up at the top of the screen. So let's try subbing in k equal 1 into our recurrence relation. That tells us that C3 is equal to C1 plus C0 over 3 times 2. So in other words, C3 is C1 over 6 plus C0 over 6. So I think we'll need one more coefficient here just to make sure that we're giving enough terms in our answer. Plugging in k equal 2 to our recurrence relation, C4 is C2 plus C1 over 4 times 3. That would be 1/12 of C2 So C2 over 12 plus C1 over 12. But we already figured out above that C2 was C0 over 2. So best way to write this is C0 over 24 plus C1 over 12. We're trying to get all of our coefficients figured out just in terms of C0 and C1. And if you wanted more terms in your answer, then you could just continue with this method, figure out C5, C6, C7, and you're trying to figure them all out in terms of C0 and C1. So let's see where this gets us. Remember that y was equal to the sum from n equals 0 to infinity, Cn x to the n. I'm going to cross that off, and let's just think about that a little bit more informally. That means y is C0 plus C1x plus C2x squared, etc. So now let's start plugging in our appropriate coefficients. So y is C0 plus C1x. We said that C2 was C0 over 2. So we got C0 over 2x squared. We figured out that C3 was C1 over 6 plus C0 over 6. So that's our coefficient of x cubed. And then we'll write down one more coefficient here. C4 was C0 over 24 plus C1 over 12. So that's our coefficient of x to the fourth. Now, a slightly better way of giving the answer is just to factor out the C0 and to factor out the C1. It just makes an answer that's a little bit more cleanly presented. So let's factor out the C0 of the appropriate terms. We would have 1 plus x squared over 2 plus x cubed over 6, plus we could generate some more terms in there if we wanted to. In the C1 bracket, we'd have x plus x cubed over 6 plus x to the fourth over 12, plus we could generate some more terms there if we wanted to. So this stuff in the first set of square brackets, that's called y1. That's one of the power series solutions to the DE. And this stuff in the second set of brackets here, that's called y2. That's our second power series solution to the DE. So let's scroll back to the wording of the question and make sure we've fully answered it. The original wording said, find the first three non-zero terms of y1 and y2. So let's see if we've done that. For y1, yep, we found the first three non-zero terms. For y2, yep, we found the first three non-zero terms. So we're good. So that is our final answer. Thanks for watching.